In this video, I am going to explain about design and simulation of full adder and a full subtractor using Tanner EDA version 2019.2. So this is a schematic representation of full adder we are going to use in this experiment. So in this, full adder contains three inputs, that is represented as A, B and C. The output is taken as sum as well as carry. So sum will be calculated by using two XOR gate logic. Then carry will be calculated by this combination of NAND, NOT, NOR and NOT logic. That is AB plus BC plus CA. That logic implemented to represent the carry. The print voltage command used for the plotting the output waveform at this particular position. Then this is definition for the VDD. Here it is defined as 2.5 volt. These are the input source signal for the ABC. I am giving the pulse signals. So next we can see this is the expected output for the full adder after performing the transient analysis. So the first three waveforms represent the inputs A, B and C. The last two represent the output waveform sum as well as carry. So after performing simulation we will be getting that. So next we can see how to draw the schematic diagram for full adder and how to perform the simulation using SEdit. First open the SEdit, double click the file SEdit. Now it is open. First create a folder. For that go to file, new, click new library, go to browse, so I am creating a folder, my full adder, then click OK. So it is created in this library. Then right click add library, browse. First we have to add some components required to draw our design. First add the library generic underscore 250 nm underscore devices, click OK. Again right click, add library, browse, then add the generic underscore 250 nm underscore logic gates, click OK. Then right click, add library, browse, select the folder standard libraries, select the folder MISC, click OK. Again right click, add library, browse, select the folder spice underscore plot, click OK. Again right click, add library, browse, select the folder spice underscore source, click OK. So these are the basic library components to draw our design. Next select the cell, click new view, then click OK. So in this area we are going to draw our design. Here I am using the basic logic gates representation. So this logic gate is implemented by using CMOS logic only. So the basic input library logic components are listed here. That is XOR gate, NAND gate, inverter, some D flip-flop, buffer. So these are the basic represented here. So first in our case we need XOR gate to represent the sum. So I am selecting this XOR, right click, instance, pick it and place it here. we need to XOR gate for this representation. Click OK. So next, to represent the carry, we need AND gate. Here directly AND gate is not there, so we are making the AND gate using NAND as well as NOT representation. So select instance. So place the 3 NOR gates here. You can maximize the screen using press home button. Next, select the NOT gate, that is inverter. So right click instance. So this will make the AND logic, combination of NAND as well as NOT. Next, we need OR gate. So to make OR gate, there is no direct OR representation is not there. There is NOR gate is there. So from that we can have the NOR operation. So I am taking the 3 input NOR, pick it and place it here. To make OR, I need NOT gate. So I am copying this, Control C, Control V, paste it here. So next we have to give the connections. So for that, take the wire, join the terminals. Here also we can give the connections. Take the wire, give the connections. For this OR gate. So next we can place the port. First I am taking output port, pick it, place it here. This is the sum. For carry, pick a port, output port and place it here. This represents the carry. Join these two, gate and this port using wire. Next we have to give the input port, we have to connect the input port. So input I am taking A first, rotating press, I am pressing R, it is now rotated. This is our input A. Similarly, next input I am taking B. Next, one more input is C. Then take the wire, give the connection A, this XOR gate input. Next, we can also connect this B. This XOR gate, this C to XOR gate. So now sum is over. For carry, First one is AB, that is take the A. First AND gate logic is represented by A into B, AB over. So next one is BC, this is B, BC. Next one is CA. CA connected. Then we can take A from here. Press home button. Now it is fitted to screen. So this is the diagram. Then for going for simulation, we need some input signal for this logic. So the input first we can give by using input source. So from here we can directly make the symbol also, or directly you can do simulation from here also. In this experiment I am directly doing simulation from here itself. So first go to spice source, select the V pulse, instance, pick it and place it here. We need 3 pulses. Then this pulse we can join together. Before that we have to connect the ground. Select the MISC plus ground. Select the ground instance. Pick it, place it here. Connect the ground. So next take a wire, join these two with this input. Similarly for this from here. Next we have to define the VDD. For this XOR as well as these logic gates. Logic gates only a symbol only, VDD is not defined, we have to define here. So take the VDD symbol, VDD instance, pick it and place it here. Then select the voltage source, spice source, select the VDC. So VDC instance, pick it and place it here. Then we need ground also. So we can copy this ground, Control C, Control V, paste it here. Here change the voltage. We can operate with 2.5 volt. I am giving the voltage 2.5 for VD. Similarly, these 3 input source here by default is 5 volt. We have to change to 2.5. This is 2.5. Second signal, this is also 2.5. C input, that also we can take it as 2.5. The 3 inputs we have given input voltages 2.5 voltage maximum value. Next, to input all the combination we have to provide 0, 0, 0, 0, 0, 1, 0 1 0 etc. 1 1 1. For that we have to make the some alter arrangement in the pulse. So if you click the first pulse we can give it as pulse period, make it as 100. So alternatively this pulse will automatically change. Second pulse we can make it as 200. By default it is 200 only. Let it be there. No need to change anything. Next, take this input pulse C. Here make it as double time of this 400. So automatically this value also change. So now this is 100, 200. This is 400. Now first 400 time period will get all the combination. For that setup only I have changed here. Here we have to add the print voltage command. Spice plot, select spice plot, select the print voltage print, select the instance. So to see the sum output we need one print voltage, to see the carry output we need another one print voltage, then to view the inputs we can also have the another one print input. Here also print input we can place it. Next, for this C input place it above for the print voltage. So next go to the setup simulation, click the transient analysis, give the stop time as 400 nanosecond, time step as 4 nanosecond. Then click general. We have to add the library generic underscore 250nm dot lib. After that press TT. Then click OK. Then click the run simulation. So this is our output waveform for our full adder design. So first two are input, first two, 1 2 3, these are inputs, this is your output, sum as well as carry. So you can see all the combinations of input is represented here. First one is here, it is 1 1 1. Now sum will be 1, carry will be 1. In this after 50 nanosecond, next logic is 0 1 1. So now carry will be 1, sum will be 0. Next this place also 1 0 1, carry 1, sum 0. Here 0 0 1, now sum 1, carry 0. So in this place 1 1 0, now carry will be 1, sum will be 0. Here again 0 1 0. Now carry will be 0, sum 1. Then 1 0 0, sum will be 1, carry 0. Then 0 0 0, we will be getting sum 0, carry 0. So this is the output of the full adder logic for all the possible combination of inputs. Next we can see how to design a full adder using Tanner EDA. So here the circuit is little bit more complex. We can go for symbol creation also. That also I am going to explain in this video. So this is the circuit diagram for the full subtractor, as similar to the full adder. Extra thing is we need one more extra NOT gate in this place. Then we have to do the set up simulation and run your simulation, will be getting the output of the full subtractor. So also other method is we can create the symbol. So for creation of symbol, first we have to make the setup like this with the logic gates. From there we have to create the symbol, then we have to apply the inputs, then we have to run your output, we will be getting corresponding response. So this is a symbol for the full subtractor for the previous circuit. Then we have to apply these three inputs and connect these outputs, we will be getting the particular output. So this is the expected output for the full subtractor after performing the transient analysis. So next we can see the video how to do the transient analysis as well as design the full subtractor using Tanner EDA. So first double click the edit. So now it is open. Go to file, new library, browse and create a folder, my full subtractor. Click OK. Now it is created. Then right click, add library, browse, go to generic underscore 250mm, add the folder generic underscore 250mm underscore devices. Click OK. Again right click, add library, select the generic underscore 250mm underscore logic gates. Click OK. Again right click, add library, browse, go to the folder standard libraries. In that select MISC. Click OK. Again right click, add library, browse, select the folder spice underscore plot, click spice underscore plot. OK. Then right click, add library, select spice underscore source. OK. So these are the basic library components required for our full subtractor design. Then now go to cell, new view, click OK. So here our design will be there. So first select the logic gates. First I am going to take the XOR gate. It is available in the last at the end. So select instance, pick it and place it here. OK. Then I need XNOR gate. Next I need. Next select NAND gate. 2 input NAND gate. Instance. Pick it and place it here. 3 NAND gate we need. Then maximize the screen by press the home button. Then take the NOT gate or inverter. Select the inverter. Pick it and place it here. 3 inverters. Then one more inverter we need for NOR operation. Place it here. Then take the NOR gate. Now 3 input NOR gate. Instance. Pick it and place it here. Then take the wire, give the connection as per the circuit requirement. First I am going to connect the output port. So output will be difference. Next output is borrow. Then take the input port, rotate, and give name as A. Next one is B. Terminals. C. First we have to join the A as well as the XOR gate for generation of difference. A XOR B XOR C. Next, for generation of borrow, first A bar B we have to calculate. For that, take one NOT gate. You can copy this NOT gate, Control C, Control V, then press R, it will rotate. Place it here. Take a wire. This is the A input. Join this. So A logic is A bar B. So A bar you can connect here. This is the input of B. A bar B, then A bar C is A bar. Take the C. Also, last one is BC. This is C. Take the B. This is B. So now representation is over. Next, we have to create the symbol. So go to cell, click generate symbol. Here with this my full order with the cell 0, the symbol will be created. then press replace all. So in cell 0 the symbol is created. This is a symbol. So next go to cell, new view. Here there is a cell name cell 1. Here click schematic, click OK. So in cell 1 it is there, cell 0. We have to drag this symbol and place it here. Now our design is available in the cell 1. Here we have to connect the input as well as output. So we can connect on output port. This you can say, I'm saying difference. Sorry, this is for borrow. Borrow. Next one is for the difference. Next for A input, take the input port. You can give A. Similarly, we have to give the B. Next, third input is C. Then take a wire. Take a wire, join this A with this port and C with this port. Then give the inputs A, B, C. So go to spice source, V pulse. You can place 3 sources. Then take the ground, MASC. We need one more ground record for the VDD definition. Place it here. Then take a wire. Give the connections. Again take a wire. Then take the source VDC. in spice source, pick it, then select MASC, select VDD. Okay, we can change the voltage to 5 volt to 2.5. We can also run using 5 also, no problem. I am giving the voltage 2.5. Similarly, for this input A, the voltage value high value is 2.5. By default is 2.5 volt. I am going to change it as 2.5. For B also I am going to change this B high 2.5. For input C 2.5. Next, for give all the combinations of all the possible combination, we have to edit this pulse. For A, I am going to change this 100. For B, I am not going to change, it is 200, let it be there. For C, I am going to change to 400. So now we will be adding all the fourth combination within the 400 nanosecond. Next, for printing the output response, we need to add spice print plot command, that is print voltage at this available at the end. Select instance, spice source, spice plot, instance, pick it. For bar also have connect the print voltage. For input A, you can place it here. For input B, for input C. So now our setup is over. Next we can go for simulation. So first set up the simulation. Click setup simulation. Here we are going to do the transient analysis. Click the transient analysis. We need to give two parameters. Stop time 400 nanosecond, 4 nanosecond. Then click general, click library, browse, select the generic underscore 250nm.lib, open, then type TT, then run the simulation. Once the design is over, no error means we will get output. Here we got the output. The input A, B, C is here. So I am dragging this in. We can also drag it, place it here first, and okay. So input in for this is the output of the full subtractor with the transient analysis. Here we can check the waveform. When it is 1 1 1, that time difference 1, borrow 1. Then if your input is 0 1 1, down the difference will be 0, borrow will be 1. Here 1 0 1, borrow 0, difference will be 0. Then 0, 0, 1. Borrow 1, difference 1. Here 1, 1, 0. Borrow 0, difference 0. Here 0, 1, 0. So borrow 1, difference 1. Here 1, 0, 0. So borrow 0, difference will be 1. Here 0, 0, 0. Borrow 0, difference 0. This is output of the full subtractor. With the help of transient analysis, we have plotted. Thank you for watching.